Hello, this is Ümit Başaran, and today I'll be presenting our work titled Towards Source-Free Machine Learning. Machine learning models often require the capability to forget data to comply with privacy regulations like GDPR and CCPA. Typically, unlearning involves having access to the original training data. However, in practical scenarios, this original data might not be available. Due to privacy concerns, data corruption, or storage limitations. So this scenario motivates the key question: how can we unlearn without access to the training data? So to tackle this challenge, our paper presents the first source-free or zero-shot unlearning method that doesn't require any original data and provides strong theoretical guarantees. Our contributions include a novel Hessian estimation method called Hessian from Forget for convex models, and comprehensive theoretical analysis, ensuring reliable and effective unlearning, and extensive experimental validation demonstrating superior performance over existing methods. Okay, so our methodology mainly focus on estimating the Hessian metrics, which is crucial for the unlearning process, without accessing the retrained training data. So to achieve this, by generating multiple perturb points around our trained model parameters, we are trying to identify the Hessian approximation that aligns best with the observed changes in loss. So the key insight behind this approach is we are trying to simulate the loss landscape with the Taylor approximation, and we are trying to estimate the best Hessian for that approximation. However, the problem is we don't have the retained data, but instead we only have access to the forget data. So basically what we did in our methodology is using forget data instead of the retained data. So to justify this point, what we are assuming is we are collecting multiple perturb points around the global optimum point. And because of the assumptions that we give about the loss functions, which is the Lipschitz assumption, uh, we are assuming that the loss change of the retained data will be close to the loss change of the forget data. Therefore, in the objective function that we have, we only utilize the loss change of the forget data, and then we are trying to approximate the Hessian that fits to that objective function. We also provide strong theoretical guarantees on our methodology. So first of all, we provide lemma 1, which provides a concrete upper bound on the approximation error of our Hessian estimation, indicating accuracy improves significantly with smaller perturbation errors, which is denoted as if it's epsilon, and larger dimensions d. So the insights for this first lemma, it's smaller approximation errors leads to better Hessian estimates, and for the high dimensional scenarios, it benefits significantly from our method since the approximation error diminishes with increasing dimensions d. We also provide theorem 1, which bounds the gradient norm on the remaining dataset after unlearning, providing theoretical assurances that the unlearning has effectively removed the influence of the forgotten data. So the key insight is successful unlearning means the gradient norm on remaining data approaches to zero, is so that it should confirm effective forgetting. So from that perspective, we gave that upper bound saying that the gradient belongs to the retained data at the unlearned model. It is upper bounded, which means there is successful unlearning using our methodology. Also, the bound tightens with more retained data, which is n minus nf. Here, n is the number of samples in the whole data set, and nf, it is the number of samples of the forgotten data. And so again, it tightens with more retained data and larger Hessian dimensions, d, which suggests our approach performs well in realistic scenarios. So before diving into our experimental results, let me briefly explain the metrics we use to evaluate our method. Starting from membership inference attack, which is MIA. So this metrics assesses how indistinguishable forgotten data is from test data after unlearning. Ideally, a successful unlearning process results in forgotten data acting exactly like unseen test data, meaning the MIA score should approach 50%, as it can be seen from the retrained line. Also, we provide test data, remaining data, and forget data accuracies. We provide remaining data accuracies to show that after unlearning, the remaining data performance is either increasing or we are trying to keep the model so that the remaining data performance will not change. We also provide the forget data accuracy to show that there should be some significant drop in the accuracy so that the test data and forget data will be indistinguishable from each other. Okay, so in this slide, our first experiment, which analyzes the effect of increasing the ratio of forgotten data. So as you can observe, our results align with theoretical expectations, which is retraining accuracy remains stable, but as the percentage of the forgotten data increases, the forgetting performance slightly deteriorates. Okay, so in our next study, we study the number of perturbations and its effect on our objective function, because we are taking the expectation over the perturb points, but we're expecting before this experiment is when the number of perturb points increases, then the approximation will be better. So as you can see again, the unlearning performance is increasing when the number of perturb points is increased as well. So finally, we benchmarked our method against existing source-free methods. So let me first briefly summarize the competing methods that we have, which is negrad, which fine-tunes only on the forget set by applying gradient ascent to increase the loss of those samples. Second, we have random labels method, which reassigns incorrect labels to the forget samples and fine-tunes on that corrupted data. We have JIT, which stands for just-in-time unlearning, uses Lipschitz regularizations to stabilize output on perturbed forget data. We have adversarial methods using adversarial examples with weight importance scores to preserve performance on retained data while forgetting. And finally, we have our method, which is unlearned minus, again used on the forget set to estimate the retained SCNM performs unlearning. So from this table, we can say that it clearly outperforms our method, all other methods in accuracy metrics, and achieves a near ideal MIA membership inference attack score, indicating effective and privacy-preserving unlearning. In summary, in this work, we have presented a robust and theoretically grounded source-free machine unlearning method. So thank you very much for listening to our presentation. If you're interested in reading our full paper, please scan the QR code here, which will redirect you to the paper. Also, feel free to reach out if you have any questions or comments on this paper. Again, thank you very much for listening.